So the first kind of test I want to look at is non-parametric correlation test. So this can apply to any set of data you have. You don't need to have any kind of normality. So eventually I'm going to take you through both the non-parametric and the parametric version. The non-parametric version is called the Spearman's rank correlation. So it just depends on you ranking the order of the data. So the null hypothesis is that there's no correlation between variable 1 and variable 2, and the alternative hypothesis is that there is a correlation between variable 1 and variable 2. What you do is you take all the numbers for your x and y coordinate and you replace them by their rank, ranking them from the smallest to the largest. So the smallest is rank 1, second smallest rank 2, all the way up to the biggest thing, which will have rank n depending on how many data points you've got. If two of them have the same numerical value, then you split the difference in the ranks. So if their one was going to be the 5th and the 6th, then you give each of them rank 5.5. If you've got 3 data points that share the same thing, so the 5th, 6th and 7th, then you would all rank them all as 6. What you do is replace all the ranks for variable 1, then you replace all of the numbers by their ranks for variable 2. Don't reorder the data because that would also be pointless, because then you'd have 1 by 1, 2 by 2 and so on. And that's the thing that you're checking for. You calculate the difference in the ranks between variable 1 and variable 2 for each one of your rows, square the differences and add together the sum of the squares of the differences and check it out to this formula. So Spearman's rank is represented by rho, and it equals 1 minus 6 times the sum of the differences squared divided by n, the number of rows of your data, times n squared minus 1. You find the critical value and the threshold from tables. So let's go through an example. So here are some chickens, and they're being fed different amount of food supplement. There's 13 chickens, and they produce eggs which have different amounts of hardness. So what you're trying to figure out is there a relationship between the amount of food supplement that you give and the hardness of the eggs? So here the first chicken, the first pullet, is got rank 13 for the food supplement. It was given the most amount of supplement and also has the hardest egg. Therefore, the difference between the two ranks is 0 and the d squared is 0. The second one ranked 5.5 in terms of food supplement, but it's the 7th largest in terms of hardness of egg, so the difference between the two is 1.5. Squared gives you 2.25. The third one is ranked 9th, highest amount for food, and 10th hardness in egg rank, so that gives you a -1. Squared turns out to be 1. So you do that for all of the set of data. So once that's done, in this particular case, the sum of all the d squareds turns out to be 6. There are 13 chickens in the experiment, so rho equals 1 minus 6 times the sum of d squared, which is 6, divided by n times n squared minus 1, so 13 times 13 squared, which is 169 minus 1. So rho equals 1 minus 6 times 6, which is 36, divided by 13 times 168, which equals 0.98352. Now, correlations go between 1, which is an absolute maximum, saying that the two things are perfectly correlated. So number 1 rank is matched with number 1 rank, 2 with 2, 3 with 3, and so on. To perfect negative correlation, which would be -1. So 1 would be with 13, 2 would be with 12, and so on. In this case, you've got 0.98, which is very close to 1. And in this case, you can check the significance. So for a p-value of 0.05 and n equals 13, any correlation that is bigger than 0.566 will be significant. So therefore, the null hypothesis is rejected, and there is a strong correlation between that egg hardness and the amount of supplement you're giving them. And that correlation is represented by a Spearman's rank correlation of 0.9352.